We've been looking at the design of optical receivers from a sensor perspective, and we have so far been looking at how light is actually detected using a photodiode, a PIN or an APD, and then we looked at how it is that the photocurrent is converted into voltage using a transimpedance amplifier, which might of course also need further amplification using an voltage amplifier, and then it goes on to the analog to digital converter and data acquisition system and all that. But so far we've been looking at these signals. Let's say, for example, you have, with respect to time, you have the incident power at the receiver. Let us say it is corresponding to a signal like this. Okay, so this is what we should be detecting, but in reality, when we convert this to a photocurrent and then try to amplify that, we end up actually generating adding noise to this optical signal. So eventually, when we look at the signal, it may not be exactly like this. It may be something like this. Okay, so it's nothing but periodic. Although I've drawn it as if it's periodic, it's nothing but periodic. It's actually typically wideband noise, typically white noise. Okay, so we will look at what is, in today's lecture, we will look at what causes noise in this optical receiver. Okay, and specifically, how can we try to keep that noise that's added to a minimum, and then we will also look at potentially noise mitigation techniques to improve the signal to noise ratio. So let's move on. Let's actually try to see what are the possible sources of noise. Okay, so the first source of noise that I would like to actually consider is what is called short noise. So what is short noise? Well, when we think about light sources, so even as we speak, certain light that's incident on me, and then that's being captured using the camera. Now we look at these light sources of as constant intensity as a function of time. Okay, so we look at whatever is emitted by an LED lamp or a fluorescent lamp as being constant intensity. But in reality, that's not the case. Okay, so you have essentially the emission of the photons from this light source happening at random time intervals. Okay, so we may look at what's coming into the receiver. If this is your say your optical receiver, we say what's coming in is let's say a particular intensity as a function of time, right, as being some uniform intensity. But in reality, if you look at this from a photon picture, it is not. So if you basically say, if you split this in terms of certain time slots, it's not like you have a uniform number of photons coming within the time slot, especially when you go to time slots in the order of nanoseconds or picoseconds, where you get to observe only a few photons coming through. Okay, you will find that the photons are not like this, right? So this is what we would expect if it is uniform intensity, like some constant number of photons per unit time per slot that we are looking at. Instead, what we will see is it could be so once again, if we look at these time slots over here, in reality what happens is it could be 4, it could be 5, it could be 3, it could be 2, it could be 3 again, and so on, right? So in reality, when we look at the corresponding signal, the signal might actually look like, and so on, right? So this is basically the number of photons, right, per unit time window may be varying with respect to with respect to time. So so this is as a function of time, and what we are looking at is now the photocurrent that's generated, IP of t, right? That photocurrent may actually be varying with respect to time because of the random arrival time of photons. Okay, so this short noise is essentially due to random arrival times of photons at the receiver. Okay, so and it's actually characterized by Poisson statistics. Okay, so yeah, you would say if you can only talk in terms of mean number of photons per time slot. So the mean number of photons in this case may be still 3, but when you actually look at what's happening per slot, it could be something like 2, sometimes it could be 5 times, it can be even 0 sometimes, and so on. So you'd have this wide fluctuations in the number of photons that are coming in, and that fluctuation is more when you have more mean number of photons. Okay, so so that's what we're talking about as it's what we're characterizing as short noise. So let's actually try to quantify that. So if you were to quantify that, you would typically look at the variance of this noise. So the short noise variance let's call it sigma square. So where do we get that from? Well, we can actually get it from the photocurrent that's generated because of the arrival of the photon. So you can say it's an ensemble average of is square of t, where is corresponds to the signal that photocurrent that we are generating. Now, if you want to quantify that, you can basically say that this is nothing but the autocorrelation of this photocurrent. So you have is of t correlated with is of t plus tau when tau actually goes to 0, and whenever we talk about autocorrelation, we actually use what is called the Wiener-Khinchin theorem. So we know that the autocorrelation and the power spectral density are Fourier transform pairs. So you can express this as over a bunch of frequencies from minus infinity to plus infinity of the power spectral density SS of f corresponding to the short noise process e power j 2 pi f times tau. Now, of course, we want the variance, which means that tau is actually equal to 0. Okay, so you can neglect this, and then you have just this quantified in terms of the power spectral density. Now, when we talk about the power spectral density of this Poisson process, we you can just draw this over here. So it will tend to be, so SS of f as a function of f. It will be sort of a white noise. So it will be corresponding to just some constant value across all frequencies, and that constant value is going to be dependent on the amount of power. It's dependent on the mean number of photons. Like I said, it's seldom this, right? It's not, the mean number is not same. It's varying as a function of time, and the corresponding power spectral density is having a value given by Q times IP, where IP is the photocurrent that we are generating. So more the photocurrent we are generating, or more is the number of photons that's incident on the photodiode, more will be the corresponding variance. So this is integrated over all frequencies, but the frequency of interest as far as the optical receiver is concerned is only the optical receiver has a certain bandwidth, right, delta f, right. So it's only over that, although we say minus infinity to plus infinity, it's effectively over minus delta f to plus delta f is what matters. So you essentially have 2q IP multiplied by delta f. So let me just write it out again. Sigma s square is given by 2q IP multiplied by delta f. This is what we call as short noise. Okay. Now, that is actually representing the noise that we get when light is actually incident on the photodiode, but you could also have noise similar, that has characteristics similar to short noise through thermally generated carriers. So even when there is no light falling on the photodiode, just because of thermal excitation, you could have electron hole pairs, and you could have a certain photocurrent because of that, and that is what we call as dark current noise. Which is due to thermally generated electron hole pairs. So obviously when you have a condition where your photodiode is cooled, okay, to a very low temperature, then the thermal energy, the corresponding thermal energy is low, and because of that the dark current noise is also low. So that's actually a very nice way of making sure the dark current is actually a relatively low value. But if you include this in the other expression, we say that the short noise variance is not just IP plus you have this ID which corresponds to the dark current noise as well. Okay, so that is something that you have to take care of, and it's actually in some ways a fundamental limitation, because even when you have no light incident on the photodiode, you still have this dark current noise, and so that will be the noise background that you are working with here. So you're not going to be able to go below that noise background. Okay, so that is actually short noise. You can say that is what you would see or expect when you have a PIN photodiode, but we've been talking lately about APD photodiode. So what is the short noise corresponding to APD, right? When we talk about APD, we have what's called a APD multiplication noise, right? That is also come into the picture. So why do we have a APD multiplication noise? Well, we already recognize that the multiplication process, right, the avalanche process, the multiplication process is random in nature, right? We said you may have a mean multiplication factor of say 10, but it's not 10 all the time. At some instant it may be 10, but some other instant it may be 7, or some other instant it may be 12, and so on. So there could be changes in that multiplicative gain value, because you're not able, I mean, it's a random event. The impact ionization and the avalanche gain that you get because of that is a random event. Okay, and what we also saw was that if you have both carriers participating in the multiplication process, the corresponding variation in the gain is even more. Okay, so this scenario is accentuated by initiation of the gain, of the multiplicating gain, by both carriers. So remember, that's where Ka, the value of Ka becomes important. Ka, which is the ratio of the impact ionization of holes to the impact ionization coefficient for electrons. We want that to be as far away from 1 as possible. So that is also playing a role in this. And of course, we saw that this was actually characterized through what we call excess noise factor, right? We called it FA a couple of lectures ago. We were looking at what is the effect, what is the excess noise factor, and quantifying all of this is so when we look at all of this, this has been discussed in this paper, it's a fairly old paper in 1966, I think it's McIntyre et al. In 1966 had actually looked at this in the noise in an APD, and what they had reported was the noise would correspond to 2q times m square FA multiplied by IP plus IQ, sorry, what I meant is ID, that's the dark current noise, multiplied by delta F. Okay, so why is it m square? Well, basically because your photocurrent goes as is amplified as m, but what we are tracking is actually the variance. So the photocurrent would correspond to the root mean square RMS value, but if you're considering the variance, then it's a square of the photocurrent. So that's why we have an m square over there. And we saw that FA, we defined that previously, where FA is given by Ka multiplied by m plus 1 minus Ka multiplied by 2 minus 1 over m. Right, so we looked at what is the effect of FA. So if we so this is actually a generic expression which holds good for both APDs as well as PIN. For a PIN photodiode, FA equals to 1, M equals to 1. So then you just get what we have over here, right? This 2q multiplied by IP plus ID multiplied by delta F. Okay, so this is actually one of the key noise processes that happens in the receiver, and this is happening right at the photodiode. Okay, so in some ways you can say that whatever noise that you accumulate here is going to be propagating through the entire optical receiver, because beyond this you have the TIA and maybe other voltage amplifiers and so on. They are only going to multiply this noise. So this is one of the fundamental limitations as far as an optical receiver is concerned. You're not going to be able to get around it, and this once again is because of the fact that we have random arrival of photons at the receiver, and that is what is initiating this noise process. Okay, so now let's move on to another type of noise that we get to see in typical receivers. This is what we call as thermal noise. It's also called as Johnson noise in certain books. So what is thermal noise? What is it due to? Well, it's due to random. So it's due to random thermal motion of charges, say electrons, in a resistor as it actually goes through a resistor. Okay, so once again what we are saying is when you have a current going through the resistor, we would like to think of it as if you take any small interval and you look at the number of charges that are present within that interval, we like to think of it as a constant value, but when it goes through the resistor, what comes through the resistor is going to be not a constant value. It's going to have some variance in the number of charges that are coming through. Okay, so this is what thermal noise is all about, and like the name suggests, it's dependent on temperature, right? So in fact, if we go through what we did previously, we said you can quantify this thermal variance as once again minus infinity to plus infinity st of f e power j 2 pi f tau df, right? If we can quantify this, well, that is of course what you get when tau equal to 0. So this exponential goes away, and then you're just integrating over st of f, and st of f is once again it's characterized by a white noise. So you will find that St of f as a function of f is like this, and the value of this is going to be given by 2 kBt over the value of the resistor, which we generally call as RL, where kBt corresponds to the thermal energy, right, that the resistor is experiencing. So in certain ways you say that if you can lower the temperature at which these components are kept, these resistors are kept, then you also you can reduce the randomness in the flow of charges and the number of collisions essentially that's happening in this resistor. You can reduce that, and through that you can reduce the overall variance. So if you plug this in here, once again what you get is sigma t square is equal to 4 kBt, where kB corresponds to the Boltzmann constant divided by RL and multiplied by delta F. So the other factor of 2 that we got here is just because of the fact that it's a two-sided spectrum that we are looking at, so we are integrating over that. Okay, so this is another fundamental limitation that we have as far as an optical receiver is concerned. Okay, so this is when you're looking at this, you are saying, hey, it looks like higher the resistor value, lower will be my variance, and so what I want to pick is a higher resistance value. So for example, in a transimpedance amplifier, you say that feedback amplifier is my load resistor, and then if I increase that feedback resistor, it's actually good. But mind you, that's actually not a true picture to look at, because when we are looking at this noise, this is actually referred to the input. So these are all what's called input referred noise. So if you want to do a proper noise analysis, let's actually look into that a little more detail. Let's say that when we consider the noise analysis of the optical receiver, you want to actually take whatever noise that you have in the receiver and refer everything to the input. Why do we want to do that? Well, if you have done all your noise reference at the input, then you can just multiply that by whatever gain of your receiver, and then that's what you get at the output. So typically, like we've been talking about, it's a transimpedance configuration, which means that all your noise is referred at the input as a photocurrent, something that's adding to the photocurrent, and then you have a certain transimpedance gain, and so what you eventually get at the output is going to be a voltage corresponding to that whatever noise current that you have. So in our circuit, we have, let's say, these current sources. So what are these current sources? Well, one of this you can say corresponds to the short noise. Okay, so now we have defined what short noise is, short noise variance is. So variance once again is nothing but ensemble average of Is square of t, right? So similarly, we have defined IT that corresponds to the thermal noise. Similarly, you can also imagine that you have a certain noise because of your op amp, because at the end of the day, when you look at what's inside an op amp, it's a bunch of transistors, resistors, those sort of circuits what you have. So each of those resistors in the op amp is actually generating noise. Okay, so that's once again like what we talked about, is because of the thermal motion of this thing. So this IT is corresponding to all the external components that we have, but this current here I would say is because of the op amp. So I'm calling this IOA. Okay, so all this are going into some transimpedance amplifier with a gain of RF, and then what you are getting at the output of this is a certain voltage, a noise voltage En. So you can just say this is actually the RMS noise voltage that you get at the output. Okay, so this is what we call as input referred noise. Okay, so you have taken whatever is happening in the circuit, you have actually just referred everything to the input. So now this is actually just an additional term to your photocurrent, and then it's creating this noise. So if we were to quantify En now, you would say this is corresponding to multiplication of whatever noise that we looked at before. We looked at the thermal noise and we looked at the short noise, right? So I will represent all of that along with it's all multiplied by RF. So like we talked about before, it's if you were to consider thermal noise, it's 4 kBT over RF, because RF is the resistor that we are considering in the feedback circuit, multiplied by delta F multiplied by RF square, because this actually corresponds to the variance. Okay, and what we are actually interested in is in the RMS value. So then this is going to be this variance multiplied by RF square, and then you're taking a whole root. Okay, so this is important to understand. These processes that we are talking about, these are all independent processes. One is not dependent on the other. So when you have independent random processes that are adding together, so let's say you have two Gaussian random variables that are adding together, what happens? Well, the variance of these individual processes is going to add. Okay, so now we are considering three different processes, okay, which are independent of each other. So the variances corresponding to each of these processes are going to add, and then you're going to take a whole root of that, and that's when you get the RMS of the combined noise. So that's what we are doing. So this we realize is corresponding to sigma t square, and similarly you're going to have another factor which is 2q multiplied by m square fa, right, multiplied by ip plus id multiplied by delta f, and that again is going to go through a gain of a multiplication of RF. So you have RF square coming into the picture here, right? So this once again is what we are calling as sigma s square. Okay, so we have basically both these variances adding with respect to each other. And then you also have like we talked about this noise due to the op amp itself. So that is actually quantified as plus IOA square, which is the op amp current. Here the op amp characteristics are typically represented in terms of the current noise density. Okay, so that's what IOA correspond to. It's the current noise density of the op amp. So RF square multiplied by delta F. Okay, so that is one term, and then the other term that you could also have is there could be certain voltage noise also. This is what we are talking about, current noise, but there could be a voltage noise also. But when we talk about voltage, the transimpedance amplifier from a voltage gain perspective is a unity gain amplifier. So if we are talking about voltage, so this will be EOA is the voltage noise density. So EOA square multiplied by delta F is what we have. Okay, so we have basically a common term coming out. So EN RMS can be written as, so you take out RF is one common term, that's a multiplicative gain that we have for the transimpedance gain, multiplied by this root of delta F is once again common across all of this. Then you have root of, you have 4 kBT over RF, right, plus 2Q M square FA IP plus ID, that's your short noise current density, right, plus you have IOA square, okay, plus EOA, that's the voltage noise current density divided by RF square, because you have taken out RF, so you'll have to compensate by keeping that RF square. So this actually is representative of all the noise sources as far as your optical receiver is concerned. Right. So this is essentially it's contributed by the thermal noise. Once again, if you look at the overall effect of thermal noise, this is what we were talking about before. It's RF square by RF, so it's actually a multiplicative factor of RF. So it is wrong to think that larger the resistor you go to, lower will be your noise. So it's the other way. When you go to higher value of resistances, as far as the transimpedance gain is concerned, you're going to have more noise at the output in terms of the voltage. And then you have the short noise component, and then the op amp contributions. Okay, so these are what will essentially make your receiver behave in this way. So the output voltage corresponding to your receiver is going to be generally noisy in nature, and of course we will see how to reduce that noise. When we consider op amp noise, I can tell you, I mean, we can make one generic sort of comparison. So if you look at, let's say, the gain of an op amp, and with respect to the frequency that we have, the frequency of operation, let's say in megahertz. Okay, typically we look at it the other way, gain as a function of frequency, but just flipping the axis. Hope you don't mind that, but effectively the gain is going as 1, 10, 100, 1000 and so on. And if you look at what typically happens for say a BJT based transistor, so I'll use a different color for that. So if you have a bipolar junction transistor based op amp, they will typically have a characteristic like this. Okay, so if you look at a particular op amp, let's say a BJT, one example is OPA 846. So if you consider OPA 846, you have noise current density that is in the order of about 2.8 picoamp per root hertz. Okay, and of course this is capable of giving reasonably good performance. This is around 200 to 300 somewhere over there megahertz. Whereas when you consider a FET type amplifier, the FET type amplifier is typically lower this frequency response. So this is typically about a value of 150. But if you look at FET type of amplifier op amp, field effect transistor based op amp, example of that is OPA 657. We looked at 656, 657 is in both the same family. But when you look at the noise current density, the noise current density is in the order of 1.3 femtoamp per root hertz. Okay, so clearly an FET type op amp is going to have much lower noise current density compared to a BJT op amp. So BJT is able to possibly give you better frequency response, but when it comes to actually the noise performance, a FET amplifier is actually much better. So a lot of these optical sensor applications, we actually try to get a FET type amplifier, especially at the front end, because that's very important. The op amp that you use as, for the TIA, that has got to be very low noise, as low noise as possible, because of the fact that any noise that's generated there is only going to be further degraded in the subsequent stages. Okay, so we'll have to be very careful about that. Okay, so we will look at all this, how an optical receiver works, and what are the typical noise sources in an optical receiver. But we will go on to looking at how to use these optical receivers, how to mitigate this noise, and so on. And before we go to that, we will also look at what are the typical specifications for any optical sensor. We will look at it next.